Alright, so now what we're going to do is do a couple of extra practice problems with what Chapter 5 is based on. So electrons in atoms and just a couple extra practice problems. Alright, so the few real key mathematical formulas to remember for this chapter deals with the speed of light, frequency, wavelength, as well as Planck's formula, Planck's theory, which is the energy. So let's go ahead and write those two formulas down. We get the speed of light is the wavelength times the frequency. Of course, Planck's is the h times the frequency. In both of these, we should be aware of what the constants are. 3.00 times 10 to the 8th meters per second is the speed of light, and h is 6.6262 times 10 to the negative 34th joules seconds. Constants that we do need to remember. The other little wrinkle in terms of using this these formulas to solve is the electromagnetic spectrum, and even more specifically the colors of the rainbow, the visible light spectrum, and knowing what their wavelengths are. If I were to ask you to solve for an energy associated with a X-ray on one end, or if I asked you to do a TV wave on another, I'd have to give you the wavelengths. Here we should know that it basically goes from 400 nanometers at the violet end of the spectrum to 700 or so nanometers at the red end, pretty much going up by 50s. All right, and give or take, it's certainly fair for what we're going to take a look at. So if I were to do a practice problem here, and I said that we had a blue, green light, it could be a copper being expressed in a flame test, and I wanted to know what the energy associated with that would be. Well, again, you know that I'm a big fan of writing down what you're solving for, what you're given. If we're given blue-green, we really don't have any numbers yet, but we should know a number. We should know the wavelength by knowing our visible light spectrum. So if I go blue-green, go 450, 500, 550, then basically we're probably safe with saying 525 nanometers. So this would be a wavelength of 525 nanometers. Okay, now if I'm solving for my energy, I'm going to be using this formula, definitely, because that's the one that has the energy in it. But to get there, I need to know the frequency, and I don't have that, but I can use the first formula, the speed of light formula, and solve for frequency with our wavelength and speed of light, and then solve for my energy. So as you see, I've written down what's given. I'm going to bring this formula over here and rewrite it. The frequency is going to be the speed of light over the wavelength. So the formula is 3.00 times 10 to the 8th meters per second over 5.25 times 10 to the negative 7 meters. Hopefully we know why I changed that. I changed it because my wavelength was given in nanometers, but my speed of light, of course, is in meters per second. So since it's in meters per second, I need to divide that also by meters. The conversion nanometers to meters is 9 places moving, but because it's 525, I'd go 9, but I'm only coming back 7 to write it in scientific notation. So that's why it's negative 7. If I now solve for that on my calculator, and again, I remind you, when you type it into your calculator, you're just going to use the EE key, 3.00 EE to the 8th divided by 5.25 EE negative 7, it equals 5.71 times 10 to the 14th, 1 over S. Again, 1 over S is cycles per second. That gives me my frequency. Therefore, I can use the energy formula now. Energy is equal to the Planck's constant times the frequency. E is equal to 6.6262 times 10 to the negative 34th joule seconds. times, bringing that down now, 5.71 times 10 to the 14th 1 over S. Multiply that on my calculator. I've already got that 5.71, so I'm just going to multiply it by 6.6262 EE negative 34. I get an energy associated with this blue-green light as 3.79 times 10 to the negative 19th joules. Nice box around my answer. And that's how you would solve using these two formulas.